Hi there. In this video, I'm not going to show you an example of a worked out inclined planes question. I'll save that for our next video. In this video, what I'm going to do is explain where it is all those formulas come from and how the physics changes when you go from friction of pushing a box on a regular surface, on a flat surface, to one that's on an incline or up a ramp, or what we call an inclined plane. Okay, so let's set up. You see a crate that's here and it's sitting on a level surface. So if you were going to apply a force to that, so we have an FA we would go have over, it technically should be just level to the plane, and we'll call that FA for an applied force on that. And then what you would have happen is you'd have friction pushing back against you. And we'll label that friction as FF. So what you would have, or how we determine FF, we already know that you would have gravity pulling straight down, and you would have a normal force of the surface pushing back upwards on you. We label this as the weight. We call it FG. The other force we would label as F capital N for a normal force that is pushed up. I guess my angle's not quite perfect. Move it a little bit, maybe not. Okay. So a normal force up and gravity downward, you would be pushing with an FA to the right and FF is to the left, opposing you. So that's all well and dandy. You could figure out an FNet for this question and everything would be great. Now, something strange happens, however, if we turn this on an angle. So if all of a sudden this is sloped ever so slightly, and what happens now is there's a little bit more going on. I'm going to ungroup this, and so we would see if this was at an angle coming across, so you'd have some angle theta, it doesn't matter what it is. You're now pushing with your FA. This is up the plane. It's in this direction. It's not to the left anymore, or to the right. It's not straight to the right because it's up the plane. And the friction isn't this way, it's down the plane along that arrow. It's now on an angle compared to what it was before. This normal force should be a 90-degree angle to the surface still, and when it twisted, it didn't quite come out that way. So if we moved it just a little bit so it would look that way for an FN. So this is still a normal force, is a perpendicular to that surface, so it's what the ramp pushes back with. But we get a problem with the way gravity is drawn here. Gravity doesn't change just because you inclined the plane. Gravity is still a force that's straight down towards the center of the Earth. So our problem now comes from the fact that the Fn and the Fg do not balance anymore. They're not pointing in the same direction. So we can't set the normal force equal to gravity like you did in previous questions. You can't do it anymore. So we have to resolve some vectors. Okay, so now if you were a person pushing on this crate, trying to hold it there and pushing like crazy, you're pushing with this FA that's up the plane, and friction would be pushing back against you once it's moving, but there's also part of this gravity is pulling that down as well. And but it's not all of the gravity because you're not picking it up. So it's not this vector that's adding to you, it's the part of that vector that's down the plane. And so we have to then redefine this gravity, or at least break up gravity. I'm going to move the FG to here. And we have to break this gravity up into part that's perpendicular, 90 degrees to the surface, perpendicular, and part of it that's parallel to the plane. So that this arrow here, it should be parallel to FF, and it should be parallel to FA. So we're going to call, since it's the parallel force, we're going to call this one FG parallel, and this arrow that comes down is going to be FG perpendicular. Now, you can just trust me on this, it's a matter of similar triangles. The angle of the plane is going to be the angle in here in the triangle, and that'll be there every time. And it has to do with the parallel lines, the perpendicular lines, so it all works out. So we now could figure out our total forces up and down the plane by adding forces. Let's say if we wanted to figure out the forces up and down the plane, you'd have an applied force, Fa. This is up the plane. You have friction fighting you, Ff. And you also have part of gravity fighting you, Fg parallel. All of those forces you could add up to get an overall or a net force. So what we used to just have as F net is Fa plus Ff, we now have part of gravity fighting us on the push up and down the plane. There's an Fg parallel to consider. Also, what you used to have before, you used to say that Fn was equal to Fg, that this Fn was equal to Fg. Well, now it's not, but from the diagram, I'll change colors, you could see that the Fn looks like it balances Fg perpendicular. Not quite, because I haven't drawn it perfectly, but if this was perfectly drawn, it should be perpendicular to the surface, and the normal force is also perpendicular to the surface. So the other formula you come up with is that Fn, normal force, is going to be the same as Fg perpendicular. So what are these values for Fg perpendicular and Fg parallel? Well, if you resolve the vectors like we've done in class, then you should be able to take the hypotenuse of the triangle and figure out the sides using the sine of theta and the cosine of theta of the angle. So this perpendicular side here is adjacent to the angle, so this is going to be Fg cosine of theta, and the parallel one is going to be Fg sine of theta because it is opposite across from the angle itself. So we have Fg cos theta and Fg sine theta. So all I want us to consider before I start throwing numbers in, I'm going to erase some of this and we're going to draw what happens if the angle gets bigger. So now that means if I take this and we group it all and twist the angle even bigger, and now take a look at what these forces would look like. So now it's a huge slope. Now if you were pushing on this, you would have to be really, really pushing hard because you're carrying more of the weight of that crate. So your Fa up the plane and your friction would oppose that motion. So Fa is up the plane, Ff is fighting you, and my gravity here is still straight down, so I have to draw it straight downward. This is Fg. Well, now, perpendicular to the plane, parallel to the plane, you can see that Fg parallel is now much longer. It's a bigger force. You're carrying more of the weight. So all that changes in this picture, if I put the dotted arrow in and make the theta, the angle, bigger, then this angle gets bigger. And what happens is you still have the same picture. Fg perpendicular and Fg parallel. The Fg perpendicular now is a smaller vector than it was before, and the Fg parallel here is a much longer vector. Okay, because if you're going up a steeper ramp, you have to carry more of the weight. You have to fight more gravity than you did before. So the steeper the ramp, the more Fg parallel there is. The formula itself doesn't really change. F net is the applied force and the frictional force and the parallel part of gravity only, just the parallel part. And then there are other ones where the normal force of the plane is now dictated by Fg parallel. Or perpendicular, I keep saying it backwards. The Fg perpendicular and Fn balance each other out. The only other formula that we have to figure out when we get into our example is this frictional force. If you remember from before that the frictional force was mu times the normal force. Well, the good news, that's still the same formula. Ff equals mu Fn. But our Fn is now different. As we just said, Fn is not Fg. It's now the perpendicular component of Fg. It's just this part of the triangle. So FF is now going to be mu times FG cos theta. If you remember from our last one, this was FG cos theta, and this was FG sine theta. So you have very much the same formulas as before, but now we just have cosine of theta and sine theta put in the appropriate places. It's really important that you try and visualize. The pictures drawn are going to be important. And even with my F nets, remember, if you're looking, you see that I have added up. I said FA is F net is FA plus FF plus FG parallel. But clearly on the diagram, FF is a negative because it's fighting you. And FG parallel is a negative because it's fighting you. So when you plug those numbers in, you're going to make these negatives. You really have to watch the signs and be careful. So that's the primer for this. So you're going to see where some of these formulas come from in the very next video that I do, where we work out examples.